All right, here we go. Organic chemistry. So just some basics about organic chemistry. Organic molecules need to contain the element carbon. They usually contain some number of hydrogens. There are many more organic compounds than inorganic compounds because of carbon's ability to form single, double, and triple bonds. Carbon can also connect to itself to make chains, rings, or branched structures, and this allows for a lot more different kinds of molecules rather than inorganic things which contain usually metals and nonmetals, and there's only so many options for those. Organic molecules are made up of all nonmetals, so they are typically covalent bonds, so sharing electrons. Most organic molecules behave like nonpolar molecules, so they have relatively weak intermolecular attractions and relatively low melting and boiling points. As the molecules become larger, the van der Waals or dispersion forces increase because remember, the bigger they are and the more electrons they have, the more dispersion forces they're likely to occur. Some of these organic molecules do have some hydrogen bonding or dipole-dipole bonding depending on what substituent groups they contain. Carbon has 4 valence electrons, which you should know, and will make a total of 4 bonds. Since it's in period 2, carbon cannot accept more than the 8 total electrons, so 4 bonds is kind of its limit. Other elements that are usually seen in organic molecules are hydrogen. They can only make 1 bond, oxygen, which typically only makes 2 bonds, and nitrogen, which typically only makes 3 bonds. Hydrocarbons are the simplest class of organic molecules. They shockingly only contain hydrogen and carbon. There's 3 different homologous series of hydrocarbons called the alkanes, alkenes, and alkynes. And if you remember from honors or regents, these just differ in terms of their bond structure. A homologous series is a group of organic chemical compounds, usually listed in order of increasing size, that have a similar structure and similar properties, and they only differ by the number of carbons that they have. So for example, these are alkanes. We have methane, ethane, and propane, so they're all very similar in how they behave, except they keep getting bigger and bigger, so their van der Waals forces increase as they get larger, so their melting points, boiling points would be slightly different, but they're all kind of similar. The homologous series of hydrocarbons, again, are there. Alkenes have at least 1 double bond, and alkynes have at least 1 triple bond in them. Alkynes are the most reactive, while alkenes are the least reactive, and that has to do with the fact that alkynes, you can split that triple bond and create places for more things to bond in there, so it allows them to be more reactive. Alkanes are kind of all filled up, which are also referred to as saturated hydrocarbons, so they're not very reactive. In order to name hydrocarbons, we have prefixes that go along with that. These are the first 10. This is what I expect you to know, and you will again have your Regents reference table available for your test on organic. They do go larger than this, but these are the ones I expect you to know. For example, this one here has 5 total carbons, so we would use the prefix for pent. And then we would have to look to see what kind of bonds are in there. Since it's all single bonds, this would be called pentane. This one also has 5 carbons, so it's still going to be using pent, but now it's got a double bond, so we would not use the ane ending, we would use the ene ending. But this one would also be called pentene. We cannot have 2 different molecules with the same name because they do not behave the same. They have different boiling points. They behave differently in chemical reactions, so it needs a different name. The difference between these 2 molecules is where the double bond is located, so that's how you differentiate them with the name as well. So you're going to add that information to the name. So the first one would be called 2-pentene because the double bond starts at the second carbon, and the other one would be called 1-pentene because the double bond starts at the first carbon. The trick is we always have to count the molecules forwards and backwards, and we always have the number at the lowest numerical location possible because molecules aren't spatially oriented. So you have to be able to recognize that 2-pentene would technically be the same as 3-pentene if it was flipped around backwards. So there's no such thing as 3-pentene. As an example, we have this molecule. This would be called 1-butyne, not 3-butyne, because if you count them, you would want to go with the lowest possible option, which would be starting at the first carbon. Isomers. An isomer is a molecule that has the same molecular formula but a different structure and therefore different properties and a different name. On the previous slide, 1-pentene and 2-pentene are isomers because the double bond is in a different place, and these molecules will have different abilities to react because of that. Between those two, which one do you think would be the most reactive? It should be 1-pentene because that double bond is simply easier to get to, being that it's at the end of a molecule and it's less restricted by the hydrogens that are present as well. So the reactivity will vary based on where the double bond or triple bond is. In addition to the bond location, the atoms themselves can be rearranged. So for example, pentane, which has 5 carbons linked by single bonds, can be rearranged in the following ways. Each of these are going to have a different name associated with them. The first thing we do is draw a box around the longest consecutively linked chain, which the first one is all 5 carbons, and that's just called pentane. For the second one, you can only get 4 carbons in a row, so that you get the prefix but, so that would be butane, and then you have to take care of what's called the substituent group, or the side chain that's coming off of it. The side chain contains just 1 carbon, so we use the prefix for 1, which is meth, but we give it the ending YL to indicate that it is a side chain, so that would be called methyl butane, and then you have to indicate where that is coming off, and this one's coming off the second carbon if you count it backwards. So again, same rules apply where you have to count it both ways and go with the lowest number. So that would be called 2-methylbutane. And then the last one, you can only get 3 in a row. That is called propane. Since there are 2 different methyl groups coming off of it, that would be a dimethyl group, and you can call it 2,2-dimethylpropane, or you can also just call it 2-dimethylpropane. This is another way to write these molecules. So if it's just carbons and hydrogens, you simply represent them with a straight line structure like this, and you can show side groups as indicated here. This one has a pretty good website for some practice with naming simple things, so if you want to give that a try, on my webpage the PowerPoint is also linked, so as a Google Slides, so you can just click on it from there rather than having to write all this down. So you should feel free to go ahead and give that a whirl if you'd like. Condensed formulas. So as you can imagine, drawing all of these out becomes really tedious really quickly. So there's a couple of shortcuts. You don't need to write out the letter H each time to represent the hydrogen. A line indicates the presence of a hydrogen. And you can write what's called a condensed structural formula, which looks at the structure and lists what each carbon is attached to. If something is coming off of the main chain, it can be put into parentheses. So for example, the isomers of pentane we looked at before, this would be CH3, CH2, 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 CH3, because it's kind of how the carbon chain is arranged. For the next one, you'll see that that CH3 that indicates the methyl group is put into parentheses, and then this one has 2 different methyl groups put into parentheses. You can condense these further by combining like groups kind of in a row and putting that in parentheses, and then kind of linking how many of those exist. There are a whole bunch of other classes of organic compounds. We talked about these in honors. This again is the Regents reference table. You have access to this for your test. So we have the halocarbons, which have a halogen attached. We have alcohols with an OH group. We have ethers that have an O in the middle. We have an aldehyde, which have a double bonded O at the end of a carbon chain. We have a ketone, which has a double bonded O in the middle of a carbon chain. Organic acids, which have the COOH group, and then esters, which have a C double bonded O and then a single bonded O kind of in the middle of the chain. Amines, which have nitrogens in them, and amides, which have the double bonded O and an amine group all connected in there. You will have the helpful hints for naming available as well from the Regents reference table. Remember, the only thing that really changes is the prefix, which indicates how many carbons you have. So just make sure you keep track of what you're counting up and use the reference table as a model to help you. So some practice using table R. I'll give you a minute to try to name these ones. The first step you want to do is to figure out which class they belong to, and then change the prefix to indicate the number of carbons you actually have, and then go from there using the model from table R. So the first example is an organic acid based on its functional group. There are 5 carbons there, so it should be pentanoic acid. The second one is a ketone based on the fact that you have a double bonded O in the middle of a carbon chain. There are again 5 carbons there, but you have to say where the double bond is taking place with the oxygen, so that would be 2-pentanone. And then the last one is an ester. You have an O and a double bonded O. Esters are the trickiest to name because you have to distinguish between the two halves of the main carbon chain because it's split by that oxygen. So one side has 4 carbons, and that's the one that's attached to the double bonded O, and the other side doesn't have that double bonded O. The side without the double bonded O gets treated as a side group, so it gets the YL ending, so that would be ethyl, and then the other side gets the O8 ending, so that would be ethyl butanoate. Some other extra information that may not have been covered in honors. There are different types of alcohols called primary, secondary, and tertiary alcohols. The primary alcohol has the hydroxyl group attached at the end of the chain, so it's only attached to one of the carbons. The secondary alcohol is attached to a carbon that's attached to 2 other carbons, and then a tertiary alcohol has the OH attached to a carbon that's attached to 3 other carbons. This is important because it tells the difference of how reactive these alcohols can be due to how restricted that OH group is. So based on these diagrams, which do you think will be the most reactive and why? So the primary one should be the most reactive, again, for the same reason that the 1-pentene is more reactive. That OH is just kind of at the end there, so it's pretty easy to access it. Tertiaries are the least reactive because it's kind of constricted by all those H's kind of hanging out. Some other vocabulary that we need to use. A chiral compound is a molecule that is not superimposable with its mirror image. Molecules that are the same in every way but are chiral are called enantiomers. So if you take a molecule like that that's got 4 different things attached to the carbon and then you take its mirror image, you'll see that they are not superimposable on top of each other, and that's what makes it an enantiomer. So they behave slightly differently. So it says, which of these represents a pair of enantiomers? The different line shapes indicate the different planes around the carbon, which is at the middle. The dashed line represents going behind the carbon, while the bolded line represents going in front of the carbon, and the flat line kind of represents being in the same plane as the carbon. Okay, so if you looked at those two, the first pair cannot be superimposed on top of each other, but the second pair can. So the first pair are enantiomers and the second pair are not. One of the cool things about enantiomers is it's really difficult to tell them apart because they pretty much have everything very similar. Their percent composition's the same, their makeup's the same, everything's the same, but they behave very differently. So one of the interesting enantiomers was thalidomide, so I want you to Google that and see what happened. It's a very interesting story. Stereoisomers is the next thing. The isomers that we discussed at the honors level just involved atoms being put together in a different order. These have atoms put together in the same order, but that arrange themselves differently spatially. For example, if you look at these two, the 2 CH3 groups are kind of going off into the same plane in the first example, and on the other side they're kind of going one up and one down. To distinguish between these isomers, we use the words cis and trans. Cis means that the more important functional groups or atoms are on the same side, while trans means they're on opposite sides. So that first example would be called cis-2-butene because it's 4 carbons in a row. You have your double bond in there, and then the other one is called trans-2-butene. The methyl groups are technically more important than just hydrogen groups. So any kind of substituent, anything pretty much other than a hydrogen is more important. Another example, you have cis-butene dioic acid. This is commonly known as maleic acid, and then basically the same kind of thing, but now the 2 organic acid groups are on opposite sides of the double bond, and that's got a whole different name and will behave differently based on the spatial organization of those 2 organic acid groups. And then as a practice, which of these is cis and which is trans? Okay, so the first one should be cis because the 2 important things, otherwise not hydrogens, are on the same side, and then the other one would be trans because they're on opposite sides. Cyclic compounds are another thing we didn't really talk about very much in honors. So carbon atoms can also connect to form ring structures. Some examples of those are there. You need at least 3 carbons to make some sort of ring kind of structure, and they all get named with the word cyclo in front. You can have double bonds in here as well. They would just change the ending of that. The most important common cyclic compounds are benzenes. So benzenes have double bonds every other carbon. This is a really useful nonpolar solvent, but it's also a little toxic, so they don't use it anymore. That first structure is really a pain to draw, so they have a shorthand for it. As you can see there's two different options. If it has a circle in the middle, that indicates the resonance of the double bonds. And then if you want to actually draw the double bonds out, you can show them with the second structure that's there. When benzene or any other ringed compound has a substituent group on it, there's some new words to use. We have ortho, meta, and para. So ortho means that the two substituent groups are right next to each other. Meta means it's at position like 1 and 3, and then para is when they're like opposite each other, so position 1 and 4. Organic reactions, there are way too many organic reactions to deal with, so we're just going to look at some simple types of organic reactions. There's a website, again, after this that will look at some other reactions if you want to take a look at them. I'm just going to look at substitution, addition, fermentation, and esterification. So substitution reactions is where we basically swap something in and out. You should end up with two products since the hydrogen that was there needs to come out and bond with the other thing. This only takes place with alkanes for our purposes, so you're always going to be sticking with the single bonds. They can become more complex depending on what you're substituting, so you'll see here the chlorine comes out and the hydroxyl group goes in from the water. Addition reactions, this takes place with unsaturated hydrocarbons. You're going to take that double or triple bond that's there and you're going to split it and go down from a triple to a double or a triple to a single or a double to a single. And you're going to add things onto that original molecule. So for example, you can add the two chlorines there by taking that double bond and opening up a new bonding space. The original hydrogens that were there do not move, so you cannot put both chlorines onto one carbon. They have to go one on each because the bond actually splits open. Again, they can become more complex, as you can see here. But you have to start with a unsaturated bond type. Fermentation, this is a reaction where an alcohol is produced. The most common example takes glucose and adds an enzyme like zymase from yeast to create carbon dioxide and an alcohol, as shown there. And esterification is the last one. This is essentially the organic version of an acid-base reaction. Alcohols are not bases, but they have an OH kind of group, so it kind of looks the same, and they do make a water, just like we do in an acid and base reaction. You actually notice here that the acid, in this case, is the one donating the OH group, and the alcohol actually only donates the hydrogen, which is very interesting, I think. The organic acid is going to then join up with the oxygen from the alcohol to create an ester. And we have another example here. You'll see again that the alcohol donates the H, the ethanoic acid donates the OH, and then they kind of join together to create the ester by bringing that oxygen in to bond with the carbon that has the double bonded O on it. Again, this website is available from my webpage, so you can go look at it for some more organic reactions if you're interested. So your test for this unit is going to include everything on this PowerPoint as well as any information that's relevant from Regents. So please make sure you look over the Regents reference tables and make sure you know how to name things. Good luck.